Hey guys, this video is 9.8 from Calculus BC, and we are picking up on the topic of Taylor series. Last lesson in 9.7, we said a Taylor series creates a polynomial that can make an estimation for a transcendental function. We also said that the higher the degree of that Taylor polynomial, the more accurate our approximation would be. So then hypothetically you ask yourself, how many terms, to what degree would I have to make this Taylor polynomial to give me a better, and then best approximation? Well, the answer, like we've seen in the past, is an infinite amount, right? If I were to technically have an infinite amount of terms and degree, then I would have not just approximation, an actual accurate answer, an approximation that gives me the exact thing that the transcendental function would. So we're going to do something like that. And when we have an infinite amount, right, of terms being added, we call it a series. It's an infinite series. So whenever we have an infinite Taylor polynomial, that is going to be called a power series. Okay. So power series are going to give us exact values and not just approximations. Now this parentheses right here is probably one of the most important things you can write down, because when you're taking the AP test or a chapter test, all of these series are going to look identical. The power series is going to look a lot like all of these past series, geometric, P series, and so on. There is one key difference to spot that you are doing a power series, and that's that the series has two variables, okay? If it's one variable, it's a geometric, a P series, any of those that we've already learned. If there are two variables, it is a power series, okay? So a sub n is always going to be our function, and then you're always going to have a c that it is centered at, okay? So if you see an x and then a minus a number, that number is your c. If you see a c missing, you can assume that your c is 0. So real quick, before I go on to more details about how this can converge, let's look down here. The following power series are centered at blank. So here they are as their nth term, written as the infinite series, and then here they are with several terms. So look here, and look here, and take a minute if you can tell me where they are centered at, okay? Well, this first one, I don't see an x minus a number, so I can assume that my c is 0. It's centered at 0. Let's look at this next one. I can see it here and I can see it here in each term. So it's usually x minus a number. So if I'm seeing x plus, that means c must have been a negative to have turned it positive. And I see the number 1. And lastly, if I look here, here, and here, remember the formula is x minus a number. So c here is centered at 1. All right, just a quick way to spot them. So now, a power series can converge or diverge. So there are 3 different ways that a power series can converge. It can converge at a single point. You'll get just one number as your answer. It can converge within an interval, okay? Now notice I put parentheses on this side and bracket on this side. It's just an example, because when you do find an interval of numbers, you also have to test whether those endpoints converge as well. So it could converge just in the inside. It can include one of the endpoints, and that is represented by this bracket, or technically they can both be brackets and it includes both endpoints. That is something you'd have to test, and I'll show you how to do that now. The third scenario is that it converges for all real numbers. It is infinite. It converges always, no matter what number you plug in for that second variable that we were talking about, okay? All right, so when we see a power series, here are the steps we're going to take for the convergence. Step 1 is the moment we see those 2 variables in the series, we know it's power series, and we're going to automatically apply the ratio test that you've already learned, okay? From that ratio test, we're going to be able to find an interval. Remember, we are stuck with a variable in there, so we're going to create that interval with that variable. We're going to isolate that variable, okay? Then we're going to test convergence and divergence for each of the endpoints by plugging them into the original series, okay? Once we've tested and determined whether we include one, neither, or both of those endpoints, then that interval that we have, some questions ask you for what is the radius of convergence. So think, if I converge from here to here, half of that is going to be the radius. Think of like when you talk about the diameter of a circle, and half of that is its radius. Same thing here. Half of this distance of this range of numbers is going to be called your radius of convergence. So very easy questions. You already know how to do the ratio test. It's just a little lengthy, but easy steps. Looking at this first example, I have the infinite series of n factorial times x raised to n. So the moment I look at this question in the middle of a test, I see that there are two variables, and that's how I catch that this is a power series. Power series always have x minus a number where they're centered at. Since I don't see a number being subtracted, I can assume that this is centered at 0. Okay, now my step 1 is to apply my ratio test. My ratio test is the limit as n approaches infinity, the absolute value of the original with 1 being added to the ends. Be careful not to add 1 to the x, okay? Just to the ends, divided by the original. Okay, I'm going to clean this. So I can rewrite this as n plus 1 times n factorial. And I can rewrite this as x raised to the n times x raised to the first. Rewrite my denominator. And now I'm going to be able to clean out these x to the n's and these n factorials. So what I'm working with here is the limit as n approaches infinity of the absolute value of n plus 1 times x. Now, being mindful that when I'm solving a limit, I am plugging infinities into n only, okay? I cannot plug that into x. So when I plug this in, the answer to this limit is infinity plus 1 times x. I know you're used to seeing the limit as x approaches, so I would plug it in the x, but here it's n approaches, so I can only plug it here. Now, in the ratio test, I learned that if this is less than 1, then it converges. If it is greater than 1, it diverges. If we clean this, we get, I still have the absolute value on the x. I know infinity plus 1 is going to be positive, so I have infinity times absolute value of x, right? So if you're asking yourself, is this greater than 1 or less than 1? Well, at the moment, I don't know what x is. So let's start imagining if x was 1, 2, 3, 4, 5, or anything positive. Positive times infinity is going to be a greater than 1. It's going to diverge. Even if that x was negative, negative 1, negative 2, negative 3, it has an absolute value around it, which would then change it positive. Multiplying it by infinity is infinity, still making it greater than 1, which means it would diverge. But if I put a 0 in the place of x, 0 times infinity is 0, which would make that converge. So I can say that for all numbers, this is going to be greater than 1, which makes it diverge, except when x equals 0. Okay, we could say, remember, we're specifically searching for convergence here. So I know that this is going to diverge almost every single time, but now I'm setting up that inequality with x. When x is 0, this converges. Okay, so remember we said we had the scenario that it converges at one point, at a range of numbers, or at all numbers. Here's the scenario where it converges at one specific number. Now, if they ask for the radius convergence, since we don't have a range to divide in half, this is just one spot, we can either say that there is no radius of convergence or that my radius of convergence is 0. Okay, let's take a look at the next one. This next question reads the infinite series of 3 times x minus 2 raised to the n. Automatically, I see the x and the n. There's two variables. I know it's a power series. I see the x minus 2. I know that I am centered at 2. Whoops. Okay, so again, first step is apply that ratio test. Remember, I'm only adding 1 to the ends to divide by the original. Automatically, I can cancel out those 3's. I'm going to rewrite that numerator. And now I can cancel out that x minus 2 raised to the n. For my next step, I'm going to apply the limit. Now remember, this limit is as n approaches, so I can only plug infinity into an n. In this case, there are no n's to plug into. I want you to compare this to when I'm doing a limit to a constant. If I were to say the limit as n approaches infinity of 5, and there's no variable to plug into, my answer would just be 5. The same thing happens here if I have an x minus 2 with no variable of n. Since there is nothing to plug infinity into, I'm just left with this absolute value of x minus 2. So my answer is absolute value of x minus 2. Okay? Now remember, my curiosity here is about where and when it converges. In order for this to converge, it would have to be less than 1 in order for it to converge, right? I'll put converge here. Now I need to solve this inequality. Now I'm taking it back, guys, to algebra, okay? In algebra, when I solve inequalities, right, that have absolute value, I first need to move anything and everything that is outside of the absolute value. So if I had like a +2 out there or a 3 out here, in this case, I have nothing to move over. So my next step would be, if I want to drop the absolute value bars, I need to put the negative version of this on the other side. So I would have to say -1, and now I can drop the absolute value. Now this is my true statement for convergence. Isolate x, add that 2 to both sides. So I'm going to say -1 plus 2 is going to be a +1. And then 1 plus 2 is going to be a 3. That means that this converges from 1 to 3. But I'm not done just yet. My next step is to plug these two endpoints into the original function in order to test whether to include them as part of the conversion or not. Okay, so being that we are talking about x's here, I'm going to plug them in the spot of x. So I'm going to test the infinite series of 3 times, I'm going to try the 1 in the spot of the x, which this can be rewritten as the infinite series. I can put the 3 outside as a coefficient, and 1 minus 2 is just a -1 raised to n. Now, we'll multiply the 3 at the end. If I just look at this portion, this is an alternating series. It's going to alternate between +1, -1, +1, -1, +1. If I multiply the 3, it alternates between positive and -3, back and forth forever. That back and forth between two numbers, we call that oscillating. And when a series oscillates, it does not exist, means it diverges. That means we are not going to include 1, so we're going to leave that inequality as is. If 1 would have come out as diverges, we would have underlined it and included it in our inequality, okay? So now let's test the other side. Let's test 3. So I'm going to say 3 times, and in the spot of the x, I'm going to put a 3, which I'm going to clean this up. I'm going to move that 3 out as a coefficient. And now 3 minus 2 is 1 raised to the n. 1 raised to anything is just 1. So that means this series is just going to be a 1 every single time. So 1 plus 1 plus 1 plus 1, or multiplying it by 3 is 3 plus 3 plus 3 plus 3, goes on and equals infinity, which means that it diverges as well. Okay, so in that case, I do not include the 1 or the 3. The inequality stays as is. This is what is called my range of convergence. And if I wanted to know my radius of convergence, it would be half of this. So for my radius, I can say, okay, between 1 and 3, there is a distance of 2, right? And then half of that distance is 1. So my radius of convergence is 1. And we are done with this question. All right, on this next example, I look at it and automatically see two variables, the x and the n, and I can go straight to series, okay? A power series. So we always start off with the ratio test. I'm going to add 1 to all of the n's. Be careful here. Okay, I just added it to that up there. And now divided by the original. Now there is a lot to clean here. We have to be very careful. We're gonna do the keep, change, flip, and we're gonna start cleaning all of these, okay? So before I do, because of the absolute value bracket, we do not have to worry about alternating because the absolute values are gonna turn it positive no matter what, okay? So let's take a minute and start cleaning this. This portion up here, if I distribute this 2, I have 2n plus 2 plus 1. One more time, I'm distributing this 2. So I have 2n, and then I have the 2 times 1 is 2, plus another one would be plus 3. All of that is my new exponent. So when I split it, I can say x raised to 2n times x raised to 3. Okay? The same thing's going to happen in here. Okay? 2 times n is 2n, and then 2 times 1 is 2, plus that 1 is 3. Okay? So I'm rewriting it like that, not to go crazy, rewriting the whole thing. And now let's keep cleaning. We have the limit as n approaches infinity of x raised to 2n times x raised to 3 divided by, I'm not going to split this one yet until I see what's going on over here. I'm going to keep, change, flip. I have 2n plus 1 factorial over, and this one I can split, x raised to 2n times x raised to 1. Now, if I want to get this down to a 2n plus 1 factorial, I can split this guy here. 2n plus 3, 1 less would be 2n plus 2, and then one more down would be a 2n plus 1. Then I can put my factorial, and now it will cancel with that one. Okay, ran out of room there, but they cancel, and now these two cancel. So now I can say my limit as n approaches infinity of, in the numerator, I am left with an x cubed over 2n plus 3, 2n plus 2, and then also an x to the first, which, look at that, there's still one more thing I can clean, okay? I can say if there's x cubed up here and 1 down here, I can take this one out, and this can become an x squared. Now, when I plug in my infinity, this is going to be bottom heavy, all right? So if you want to, I'm going to rewrite it one more time just so you can see. I'm going to call this 1 over 2n plus 3 times 2n plus 2 times x squared. So again, this infinity goes into this portion only, which in here, it makes it bottom heavy, which is 0. So I can say 0 times x squared. So 0 times anything is just 0. And if I want to know when this converges, it has to be less than 1 in order to converge. Well, in this case, because the x disappeared, 0, no matter what the x is, it disappeared, will always be less than 1, which means that this always converges. So it can converge for all x's. Okay, another way of saying that is from negative infinity to infinity, no matter what number x is, okay? And if I cut infinity in half, I still have infinity, so my radius of convergence is also infinity, okay? So we've seen the 3 scenarios so far. We've seen at one number, we've seen when I'm left with an x and it's at a range of numbers, and then we've seen when the x disappears and it can be any number that converges, all right? Let's move on to another example. I see 2 variables, I see an x and an n, so I'm going to start off with my ratio test, the limit as n approaches infinity, absolute value of, I'm going to write the original, adding 1 to the n, divided by the original. Okay. On this first one, I'm going to change it as x raised to n times x raised to the first over n plus 1. I'm going to keep change flip, put my n up here, and then my x raised to the n down here. Now, as you get better at these, you might be able to start seeing where this is going. I see that these two cancel, and then when I'm going to plug my limit, my n's have the same exponent, so L'Hopital's rule says it's 1 over 1, and I'm left with 1 times x. So I'm going to write this all out, obviously, but hopefully you can start getting a little faster at these for the sake of the AP. So the limit as n approaches infinity, absolute value, I'm going to keep the n's together, and then times I have this x. Okay, so the limit is as n approaches, which means I can only plug in here. Infinity over infinity, I look at L'Hopital's rule, exponent is the same, so I go to my coefficient, which is 1. So my answer is 1 times absolute value of x, and in order for this to converge, it has to be less than 1, okay? So absolute value of x, 1 times absolute value of x is just absolute value of x, has to be less than 1 in order to converge. In order to drop the absolute values, I have to put plus or minus of this number. So I put the negative 1, I drop the absolute value, and 1. So in order for it to converge, here's my interval so far for convergence, right? Next step is to test my endpoints by plugging them into the x. So my first test is going to be for negative 1. So if I put that negative 1 in the spot of x, another way of writing this would be to say, I'm going to put the alternating symbol in the front and then times 1 over n. So now I need to find out if this converges or diverges. I can immediately see that this is going to be an alternating series. So first I check, is it alternating? Well, I see the symbol, so yes. Then is it decreasing? Well, if I have 1 over n, then if I start going 1 over 1, 1 over 2, 1 over 3, 1 over 4, since those denominators are getting bigger, the whole number is getting smaller, which means yes, this is decreasing. And then lastly, does the limit as n approaches infinity of the leftovers, not the alternating part, 1 over n, does this equal 0? Well, if I put infinity here, this is bottom heavy and it does equal 0. So yes. So by the alternating test, I know that this does converge. Okay, so it converges at x equals -1, which means I'm going to add that little mark. I'll do it at the bottom though, okay? Now we need to test the positive one. So we're going to plug it in to the original question. And again, this is an interval for what x can be. So I'm going to plug it into x. And I'm going to say 1 raised to n over n, which 1 raised to n, 1 raised to anything is just 1. So I'm doing, whoops, I put a 1 there, I'm sorry. 1 over n. Okay, we've seen this several times before. We know this is harmonic, and we know that harmonics always diverge. Okay, so now for my final answer, my range of convergence is going to be from -1 included, because I need to include it, and then up to 1 not including 1 because 1 diverges. Another way you can write this, guys, is you can put a bracket on -1 up until 1 with a parentheses, 2 different ways, and then my radius of convergence, well, from -1 to 1, and you can subtract, we can say 1 minus that -1 gives me 2, and then we know that half of that is my radius, which gives me 1. So 1 is my radius of convergence here, okay? And that is my final answer. Again, this one or this one, and then my radius is 1. All right, last question. This is going to be a lengthy one. So we see that there's an n and an x. We know this is the power series. We can see that it's centered at 3. Doesn't really affect our question, just so you can catch it. We're going to start off with our ratio test. So I'm going to start up here because this one is a lengthy one. The limit as n approaches infinity, absolute value. I'm going to add 1 to all of my n's. Okay, and because of the absolute value, I can automatically eliminate these -1 to the n's and n plus 1, because since absolute value, it's going to be positive anyway. And now I'm going to work on rewriting these. The x minus 3 goes to n, and we separate it by multiplication, and x minus 3 also goes to the first power. Okay, 4 to the n times 4 to the first. This changes to multiplication. My 4 to the n goes to the top. And on the bottom, I'm left with n times x minus 3 raised to n. Let's see what we can eliminate. I see these 4 to the n's, and I see this x minus 3 raised to the n. Okay? So I've got the limit as n approaches infinity. I'm going to write everything with an n first. Actually, I'll write my coefficients first. I have a 4 in the denominator, and then I have an n. And then here, I have no coefficient, just that n plus 1. And then on the numerator, I have x minus 3 to the first power. Okay? Now remember that limit, this limit in particular, we're plugging infinity into the n's only, not the x's. So now I'm doing L'Hopital's rule or horizontal asymptote rule much faster. If I look at my exponents, they're both 1. So I'm going to look at my leading coefficient, and this portion right here gives me 1 over 4, and then I'm left with, right, this x minus 3. Absolute value. I'm curious as to when this converges, so if I want to solve for when this converges, it would have to be less than 1 in order for it to converge. Okay, now remember, in order to drop the absolute value, I need to put the -1 on the other side. So now I'm going to multiply 4 to all three sides, to all three parts, or we'll say. So I've got -4, x minus 3, and +4. And now I'm going to add the 3. So I'm going to end up here with -1, x, and then if I add 3 here, I'm going to end up with 7. So far, this is my radius of convergence. Now I need to test my endpoints, okay? I test my endpoints by plugging them into the x. So I'm going to test my -1 first. So this part stays the same. And then this becomes -1 minus 3 raised to n over 4 raised to n. -1 and -3 make a -4. So this portion right here is going to become a -4 raised to n. Now that portion can be rewritten as well. So I have this -1 raised to n, and I can separate this as a -1 and a +4. So I could say -1 raised to n times 4 raised to n. And the reason why I want to do that is because I have a 4 raised to n in the denominator that this can cancel with, and two negatives make a positive, so they cancel each other out. So what I'm really working with here is the infinite series of just n. So that means if my function is n and I'm plugging in numbers 1 to infinity, I'm going to add 1 plus 2 plus 3 plus 4 plus 5 and so on and so on. So that will eventually add up bigger number, bigger number, bigger number to infinity, which means that it diverges. So we know that this diverges at x equals -1 was the one we just plugged in. Let's do the same thing for 7. My infinite series, plugging 7 into my original function, so I have -1 raised to n times 7 minus 3 raised to n over 4 raised to n. I know that this portion right here is going to give me a +4 raised to the n. So that means that this will cancel out with this 4 raised to n. So now I have -1 raised to n times n. Now at this point, I can see that I have an alternating, right? Now for the alternating test, I need to check if this starts to decrease. Well, this is an n. This is only going to increase as I plug a number in. Bigger, 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 bigger. So even though it alternates sign, it doesn't decrease, therefore it diverges. Okay, so since they both diverge, when I want to answer my range of convergence, I am not going to include the -1 and the 7, so I do not underline my inequality symbols. I could say -1 to 7 in that notation, or I can say -1 to 7 like this. And then my radius, well, it goes from -1 to 7, so I can subtract to find out the distance, and I get 8. And then half of that distance gives me 4, and that is my radius of convergence. So we've got my range, and then we've got my radius, and we're done.